Hi everyone, welcome to week 4 of Astronomy 236. In this lecture bite, we're going to be talking about general relativity and Hubble's law. So we talked about special relativity the other week, and in particular, we talked about how special relativity modified the rules of classical mechanics for objects or people traveling very high speeds at close to the speed of light. Special relativity is special because it only works for travelers who are going at a constant velocity, and it doesn't really describe accelerations, or if you remember your classical mechanics, the forces that apply things and cause those accelerations. So how can we take the theory of special relativity and expand it and think about what happens when things accelerate and even accelerate and why things accelerate? So as a reminder, acceleration is when something changes speed. So on the left, I'm showing here two cars. They start off stationary and then they accelerate and their speed increases. On the right, I'm showing a kangaroo dropping a ball. This acceleration is due to gravity, and you'll understand in a few slides why I put this particular example on. The acceleration due to the car and the acceleration due to the gravity, it doesn't really matter what causes it. All we care about for acceleration is that there's a change in the speed of something. And in both of these cases, the speed started at 0 and accelerated to have a speed greater than 0. So when we were talking about special relativity, we were thinking about people in cars and trains and spaceships that were moving at constant speeds. Now, imagine that we have a person in a rocket ship that's starting off stationary. It's starting off from the ground and it starts to accelerate upwards. So when this happens, the rocket ship starts off moving very slowly and then it gradually gains speed as it moves upwards. The person who is in that rocket feels a force. He feels that he's being pushed towards the bottom of the rocket. You may have experienced this yourself if you've ever gone on an airplane and felt pushed towards the back of the airplane when the airplane turned on its engines to start to take off. You felt that force, that acceleration pushing you backwards. You can see the same thing happening in slower situations as well. So imagine you're riding on an elevator and you're standing on a bathroom scale. That's what this fellow is doing here. He is riding an elevator from the first floor to the fourth floor. And what he's doing is he's watching what the scale does. And you can see that when the elevator starts moving, when it starts accelerating from stationary to its normal operating speed, the scale moves just a little bit up. And then when it slows back down, the scale moves a little bit down. So let's watch this again. He's now on the fourth floor. Now he's on the first floor, and his weight apparently increased just slightly. Now it's back to normal. And then when the elevator slows down, right here, his apparent weight decreased just a little bit. So the acceleration that he feels translates into a force. The idea that forces like gravity, in particular gravity that this guy is feeling on the elevator, and the forces that you feel due to acceleration are basically the same, is a really important idea for developing general relativity. This is called the equivalence principle. And the idea is that the effects of acceleration are indistinguishable from the effects of gravity. So if you put a person in a box, in this case, a teal box, just the same size on the ground on the right-hand side, or in the spaceship on the left-hand side, and you accelerate the spaceship to precisely the same acceleration as an object would experience due to gravity, the person in the box cannot tell the difference between being on a planet stationary in a gravitational field or being out in space accelerating away from his spaceship. And this implies that there's some fundamental connection. And that's what led Albert Einstein to go down the path that he did. After developing special relativity, some of Einstein's work concentrated on understanding why is there an equivalence principle? Why does gravity, the thing that holds us to the Earth, the thing that holds all of the planets in orbit around the sun, seem to behave exactly the same way as something that's accelerating? And what Einstein came up with is revolutionary. What he says is almost that gravity is an illusion. So if you have stuff with mass and energy, and you remember mass and energy are basically the same thing, they can be exchanged between each other, they actually warp space itself. And gravity is just the consequence of us moving through warped space. So here's a visualization of that in this GIF here. You can imagine that in two-dimensional space, if you move only in the plane, Earth is causing this indentation, and the moon is orbiting around because it's trapped in that indentation. This is what Einstein means when he says that mass and energy warp space-time. The mass of Earth is warping space and causing the motion of the moon to travel around it because of that warp. Here's another GIF that shows a similar thing. Here you can see three big stars, three massive stars, and you can see smaller round objects traveling around. And these round objects are essentially traveling along the contours of this warped space fabric. And the other thing that you'll notice is that occasionally there are beams of light that shine around here as well. What Einstein's theory also predicts is that light can be bent and warped by space. It moves through space the same way that particles do. And light, therefore, can be bent when it goes near a massive object. So space is not two-dimensional. Here's a more realistic understanding of what it might look like to be near a massive body in space. So here, space is a grid instead in 3 dimensions instead of in 2 dimensions. And you can see that the grid points closest to this massive star in the middle, shown in green, are stretched closer together. They're warped. It's a little bit more difficult to visualize in 3D. And here's a moving view. So if this object were moving around, you could see that this, the structure, the fabric of space warps and follows it as it does that. So this is really hard to get your mind around. So I'm going to add in a brief video interlude to hear more from Brian Greene and Fabric of the Cosmos.
Newton's stage was a huge hit. It enjoyed the limelight for over 200 years. But in the early decades of the 20th century, a new set of ideas emerged that shook Newton's stage to its very foundation. Ideas put forward by a young clerk working in a Swiss patent office. His name? Albert Einstein. Einstein grew up in the late 1800s, at the dawn of the age of electricity. Electric power was lighting up cities, giving rise to all kinds of technologies Newton could never have imagined. All of these developments tapped into something that had captivated Einstein since he was a child: light. Not light bulbs and street lamps, but the very nature of light itself. And it was his fascination with one particularly weird feature of light, its speed, that would lead Einstein to overturn Newton's picture of space. To see how, let's take a ride. Right now, we're traveling at about 20 miles per hour. And to go faster, all the driver needs to do is step on the gas, and the cab speed changes. Now, you can feel that change, but you can also see it on the cab speedometer or on one of those radar speed signs. Okay, you can slow it down now. But now imagine that instead of measuring the speed of the cab, you have a radar sign that measures the speed of the light coming off its headlights. That sign would measure the light traveling at an astounding 671 million miles an hour. Now, when the cab starts moving, you'd think that the speed of the light would increase by the same amount as the car. After all, you'd think that the moving cab would give the light an extra push. But surprisingly, that's not what happens. Our radar sign, or any measurement of light speed, will always detect light traveling at 671 million miles per hour, whether the cab is moving or not. But how could this be? How could all measurements of light speed always come out the same?
If you're running at a wall, it's coming at you faster than if you're standing still with respect to that wall. But that's not true with light. The speed of light is the same for everybody. That's really extraordinary.
So here's how Einstein made sense of this extraordinary puzzle. Knowing that speed is just a measure of the space that something travels over time, Einstein proposed a truly stunning idea: that space and time could work together, constantly adjusting by exactly the right amount, so that no matter how fast you might be moving when you measure the speed of light, it always comes out to be 671 million miles per hour.
To respect that absolute quality about light, time had to cease to be absolute, space had to cease to be absolute, and those two had to become relative in such a way that they slosh between each other.
If space and time being flexible sounds unfamiliar, it's only because we don't move fast enough in everyday life to see it in action. But if this cab could move near the speed of light, the effects would no longer be hidden. For example, if you were on a street corner as I went by close to the speed of light, you'd see space adjusting so that my cab, it would appear just inches long. And you'd also hear my watch ticking off time very slowly. But from my perspective, inside the cab, my watch would be ticking normally, and space in here would appear as it always does. But when I look outside the cab, I'd see space wildly adjusting, all to keep the speed of light constant. So with Einstein, time and space are no longer rigid and absolute. Instead, they meld together with motion, forming a single entity that came to be called space-time.
I think as we live our life every day, we live with the Newtonian picture of space and time. It's something that we are comfortable with. But Einstein was able to make reason conquer sense. And that really was the genius of Einstein.
This notion that space and time are unity, to me, is one of the greatest insights that has ever occurred in science. It's so counterintuitive to everything we've ever experienced as human beings.
And in the hands of Albert Einstein, this new picture of space would solve a deep mystery having to do with the most familiar force in the cosmos: gravity. Newton knew that gravity is a force that attracts objects to each other, and his laws predicted the strength of this force with fantastic precision. But how does gravity actually work? How does the Earth pull on the moon across hundreds of thousands of miles of empty space? They behave as if they're connected by some kind of invisible rope. But everyone knew that wasn't true. And Newton's laws provided no explanation.
Einstein found that no Band-Aid patches would fix Newtonian gravity. He had to invent a mechanism for it. He had to understand it.
After puzzling over this problem for more than 10 years, Einstein reached a startling conclusion. The secret to gravity lay in the nature of space-time. It was even more flexible than he had previously realized. It could stretch like an actual fabric. This was a truly radical break from Newton. Think of this table as space-time, and think of these balls as objects in space. Now, if space-time were nice and flat, like the surface of this table, objects would travel in straight lines. But if space is like a fabric that can stretch and bend, well, this may seem a little strange, but watch what happens if I put something heavy on the stretchy space-time fabric. Now, if I take my shot again, the ball travels along an indentation in the fabric that the heavier object creates. And this, Einstein realized, is how gravity actually works. It's the warping of space-time caused by the objects within it. In other words, gravity is the shape of space-time itself. The moon is kept in orbit not because it's pulled to the Earth by some mysterious force, but rather because it rolls along a curve in the space-time fabric that the Earth creates.
With Einstein, space became not only real, but flexible. So suddenly space had properties, suddenly space had curvature, suddenly space had a flexible kind of geometry, almost like a rubber sheet. It opens up a whole new way of thinking about reality that described the entire universe. Einstein becomes Einstein because of that observation.
Where Newton saw space as passive, Einstein saw it as dynamic. It's interwoven with time and it dictates how things move. So, after Einstein, space can no longer be thought of as a static stage. It's an actor, and it plays a leading role in the cosmic drama.
All right, now that we're back from that movie, let's move on. So when we were talking about special relativity and trying to figure out what some of the consequences of it were, we did a lot of thought experiments where there was a person shooting laser beams inside of a very fast-moving car. So let's do the same thing here, but instead of in a car, let's imagine that he's inside of this rocket that's now accelerating from stationary upwards and moving very quickly. So this guy fires a laser beam, and from his point of view, the laser travels to the far side of the rocket, and it moves in a straight line. That's because he's moving along with the rocket, so he sees it going straight. But what happens if you see it from outside of the rocket, and you see it from someone who's watching the rocket accelerate away from the Earth? So now, instead of the light traveling a straight pathway, it travels a curved pathway. And that's because at the very beginning of the fire, at the very beginning of when the laser was shot, the rocket was not moving very fast. So it didn't change its position in the vertical direction very much. But as the rocket sped up, it started to move faster in the vertical direction. So towards the end of the laser shot, towards the time when it almost was about to hit the wall, it was traveling faster in the vertical direction and having a steeper slope. So you get this curve. So light appears to follow this curved path from the point of view of someone who's not accelerating. But we just said that acceleration is indistinguishable from gravity. So what does this mean? It means that light will bend near massive objects, which is what we just talked about earlier. So that's kind of an intuition as to why this might take place. So based on this as well, because light takes a longer path inside the accelerating object, the curved path that it takes here is longer in distance than that straight path from when it was fired just from a perspective of the observer in the rocket. Following what we talked about in our special relativity lecture, because the speed of light is constant always for all observers, therefore time must be slower for an accelerating object. So for that guy in the rocket ship, time is traveling slower for him. But since, again, acceleration and gravity are indistinguishable from one another, that means that time also slows down for someone who's in a strong gravitational field. So if you are very close to a massive object, time will move slower for you than it does for someone else. If I watch you go near a black hole and come back, more time will have elapsed for me than it will have for you. And of course, this is very critical to the plot of the movie Interstellar. Okay, so what does general relativity actually look like? I'm showing you this equation. You won't need to understand much about it, but I wanted to give you an idea of just kind of the things it relates. So there's three important terms that we'll look at here. The first one on the left describes how space curves or is curved. So this is a way to describe just what that curvature due to a massive body is. This term on the right, the T mu nu, describes where matter and energy are, where things are in the universe. So you can think of this as instructing space how it must curve if this is where your matter happens to be. And then this final term on the left, and on the left-hand side in the middle, the lambda g mu nu, is what's called the cosmological constant. And we'll get to the importance of this later, and you'll have a reading that goes more in depth here. When I say this is the Einstein field equation, that's not quite right. It's actually 10 separate equations that are all coupled together and that all follow the same form. And this is just a particularly compact way of writing them. These are really hard equations to solve. They're considered to be much harder than the Schrodinger equation to solve, and solutions to these equations are fairly rare. But there are a couple of very important ones that I want to at least talk to you about. So the first important solution to the Einstein equations is what happens if there is a spherical mass that's by itself in space. This is analogous to what you have with a planet or a star. So in both of these cases, you have a sphere and it has some mass. What is the gravitational influence of the sphere on the space around it? And the solution that was come up with was called the Schwarzschild metric, which is named after Karl Schwarzschild, the person who came up with it. A fun fact is that he actually solved Einstein's equations very quickly after they were published by Einstein while he was in the trenches in World War I. So the Schwarzschild metric, in most cases, especially the ones that are similar to our own environment, are nearly identical to Newton's laws of gravity. And they only differ in extreme circumstances. So when you're very close to an object that's very massive. One of the most important differences between the solution to a Schwarzschild geometry and Newton's classical mechanical law of gravity is that objects that are orbiting stars will tend to form these rosette patterns. When they have an elliptical orbit, they won't necessarily come back exactly to the point where they started off. Instead, these objects will kind of precess around and form these complicated looking spirals. According to Newton, this shouldn't happen at all. When you have two objects close together and they're orbiting in this position, they should form this perfect ellipse, and it should always return to exactly the same point, and it will never precess around. It will never form this spiral. This is one of the first ways that general relativity was tested in our solar system, and it continues to be one of the most exciting ways to test it and push its limits and see just how good of a theory it is and just how well it describes the gravity in our universe. Another consequence of the Schwarzschild metric that you don't necessarily get from Newton's classical laws of gravity is the idea of a singularity. What happens when you have an object that's extremely dense, that's very, very tightly packed together? You have lots and lots of mass in a very small amount of space. According to Schwarzschild, what happens is that if you get close enough to that mass, you can never come back out. And inside of that mass is a single point where there's all of the matter concentrated together. This is what is called a singularity, that single point with all of the mass. And cloaking that singularity is what we call a black hole. The point of no return is what we call the event horizon. If you go beyond the event horizon, nothing, not even light, can come back out. So the Schwarzschild metric is one of the most important solutions to general relativity that we have. But the other really important one, which we'll spend a lot of time thinking about in the next couple of weeks, is a solution to the Einstein field equations where you assume that there's just some smooth fluid that fills all of space and that this fluid has some density. And the solution here is called the Friedmann equation. So that's kind of a weird thing. Why would I want to assume that we're solving the Schwarzschild equation for some fluid? Or we're solving the Einstein equations for some fluid. And the answer is, if you look at the universe and you just imagine that you take all of the stuff in the universe, all of these galaxies in this picture that I'm showing here, and you smear them all together, it would make a fluid. And it's not a bad approximation for what we actually see. Galaxies and gas and dust throughout our universe are pretty well mixed together. And there's not really many places where there's tons more matter than other places. So in general, the idea of a smooth fluid with some constant density is pretty good description of what our universe is. So really, when we solve the Einstein equations in this case, we're solving for the behavior of our entire universe. So before I go on further, I want to give a refresher on what density is. I've said this word a couple of times already in lecture, and it's pretty simple. So the idea of density is just how much matter, how much mass, how much stuff you have, and how much it weighs can you pack into a small area. So imagine that I have the same volume, the same physical space, and I fill one of those physical spaces, like 2 cubes that are an inch on each side, and I fill one of those with cotton candy, and I fill the other one with lead. Which of these will weigh more? And the answer, of course, is lead. And that's because lead packs more mass, lead packs more heft into a small area than cotton candy does. And that's all we mean by density. How much mass can you pack into some small area or some small volume? So it turns out that when you look at these equations for, or the solution, the Friedmann equations, general relativity cannot naturally describe a universe that is static, or one whose density does not change much. If you solve for this fluid and you assume that it has some density, the general relativistic solutions want for that density to change over time. And that's kind of weird, right? We think about the universe as something that's constant, that's something that's been there forever and presumably will be there forever. And it doesn't change, at least on the timescales that we're used to thinking about. So that bothered Einstein. So he worked really hard and he found a solution to his equations. It required adding this cosmological constant, this additional term in his equations that I mentioned earlier. But if you add this in, you can find a solution to his general relativistic equations that lets some constant density of the fluid of the universe exist without changing. So Einstein believed that he had perhaps found the solution to our universe because it seemed to match what everyone believed at the time was true, that the universe was constant and that it wasn't changing over time. But there was a problem to this solution as well. The solution that Einstein found is what physicists call unstable. And what that means is that if everything is perfect, if everything is left in balance, then that solution can stay in that place. But if you tilt it or perturb it just slightly, so imagine some part of the universe becomes slightly more or less dense because something has happened, some action has taken place, then that can take this perfect solution and throw it out of whack and cause all of the universe's density to start to expand or decrease. So these solutions, these unstable solutions, they may appear to work, but when you look more closely, they actually can fall apart. Meanwhile, across the Atlantic Ocean, things were changing as well. So we talked a couple of lectures ago about what happened in the Great Debate, where Edwin Hubble discovered a variable star in the Andromeda Nebula and found out that this was actually very far away. It was actually a galaxy. And it was an island universe all of its own, just like our own Milky Way is. And he did this by finding this Cepheid variable star and using the Leavitt law to measure the brightness of that star and compare that to what it really should be and measure the distance to that galaxy. So Hubble didn't stop there. He used this over and over and measured the distances to many different galaxies. And then what he did was he took measurements of the color of light, how much the spectral fingerprints of elements, the spectral lines that are produced by quantum mechanics had shifted to measure apparently how fast that galaxy is moving either towards or away from us, what the velocity of that galaxy is. And he plotted these results against each other, and he came up with this famous diagram. So on the y-axis here, Hubble is showing the speed of objects or the velocity of objects as they move away from us. So on the y-axis, the positive numbers, so positive velocities, mean that these galaxies are moving away from us, and negative velocities mean that they're moving towards us. And on the x-axis, he's showing how far away these galaxies are from us. And what he found is striking. What he found is that, first of all, almost all of the galaxies seem to be moving away from us. Only a handful of the very nearest ones are moving towards us. And perhaps even more unusual and more striking is that the further away we are from these galaxies, the faster they seem to be moving away from us. What does this mean? If you have galaxies that are spread out throughout space, and the ones that are closest to us are not moving very fast with respect to us, but the ones that are furthest away are, that seems to point towards the galaxy is all racing away from us, as if everything between them is getting inflated or expanded. So this observation, and in combination with the idea, the theory of the Friedmann equations, that points towards it being very difficult to find universes that are not static, both imply that that instead of the universe being constant and static, it may actually be changing. And in fact, this change is an expansion that's happening right now.